So this is the question in which we have to detect the cycle in our directed graph. So in my previous video I have to do this using the DFS method, but in my just previous video I have to explain what's the topological sort using the DFS and BFS method. Okay, so now come to this part. If I have to prove if I have to detect the cycle in our directed graph using the BFS method, so we can simply do this by verifying the topological sort. Means we know one thing very well, like topological sort is only valid for the DAG. Means what we can say, topological sort is only valid for the DAG case. Okay, so if I have to apply the topological sort on any of these graph, so let's say if topological sort is not verified for this, so that means it is simply the there's a what we can say, if I am to apply any of the directed case, so it means if the condition fails, so this only means that there is a cycle is present in it. Okay, so by the simply using of the topological sort, we have to eliminate, or we can simply judge whether the cycle is present or not. Okay, let's say if I have to if I am to apply the for linear cases, there's a simply topological sort is working here, and it means simply there is a not cycle here. Let's say what if I have to try applying the topological sort on the cycle cases. Let's say there is a one cases, this is simply pointing to 2, this is pointing to 3, and let's say this is pointing to 4 there. Okay, and now this is pointing to 5. Okay, now let's make since this is a directed cases, so just make this as a direction. Okay, so now this is a case. Okay, and also for the topological sort, we also need the data structure, that is nothing but the Q data structure. So now so what are the element? We have to first using the adjacency list, we write the all of the integrity of all of the nodes there. So whose nodes who have the integrity as a 0, simply push first in our the Q data structure. So there's only one node which has integrity as a 0, so simply push this in our Q data structure. Okay, so after now what we can do, simply pop this and add in our answer there. So this is our answer vector here. Okay, and like what we can say, since it can be removed, so after removing its integrity of its neighboring elements reduces by 1. Okay, so it means if I have to eliminate this edge there, okay, so its in degree, initially it in degree as a 2 there, but now its in degree become 1. Okay, now keep reminding this, its in degree become 1. Okay, its in degree always it's nothing 0, it's non-zero, it's non-zero. Okay, now come to this part. Now there is no node remaining whose has a in degree 0, so the Q is since Q becomes the empty, because the code is working till the Q become the empty there. But okay, so after the Q is empty, only the one node is adding to our answer. So that means there is not possible to do the topological sort for this case, as we already know that this is not following the DAG case, means directed acyclic graph there. Okay, so now so what we can judge from it, we have to simply write out the integrity code, or we can say the Kahn's algorithm. Kahn's algorithm is nothing but the when we do our topological sort, I can say, see, whenever we can say our topo sort using BFS method. Okay, so BFS is nothing but the our integrity method there. Okay, so it is nothing but it is called as a Kahn's algorithm. Okay, so this is our Kahn's algorithm. Okay, so this is simply the code for the, as we already know, we do in our previous video. If you don't know this, you just see my previous video where I have explained this, how to do this topological using BFS, and already I also explained in my previous videos how to do this with DFS method. Okay, so we have to make our integrity vector there with initialize with 0, calculate all of the integrities, use our Q data structure. Now what we do, we simply initialize our one variable as a count. Okay, to finally count all of the number of the nodes in our final answer. Okay, so that is nothing but our resultant vector there. Okay, so what we can say, simply traverse all of the nodes. So the whoever the nodes who has in degree as a 0, simply push this in our queue data structure. So now while queue become the empty, simply extract this node there, pop this, enter this in our the final answer. So either we can take the resultant vector or add this in our resultant vector, or either we can say since we don't need our resultant vector, we just need what are the number of the nodes present in our node, present in our resultant vector. So we just simply use our count variable increasing, means we add one node in our the resultant vector. Okay, so like we don't have to take extra vector there, because we simply want the count, whether count is equal to vertices or not. Okay, so that gives me the meaning of the detection of the cycle. So simply count plus plus. Okay, so means we have to process that node. So after removing, we go on its neighboring part, simply removing the integrity of the neighboring elements by 1. Okay, if integrity becomes 0, simply push this in our queue data structure. Okay, so after removing the, or after queue become the empty, simply check if the count of number of nodes in our resultant vector is become the equal to v, means we are able to write the troubleshoot completely. So that means it is only valid for, also only possible when there is a graph is it must be the acyclic. Okay, so it means we simply return false because we want cycle. So here we are not able to find cycle, simply return false. If that is not possible, and since this is a directed, so the only condition false in a DAG case is due to the A, means acyclic, so simply return true in that case. Okay, so what's the time complexity is? This is nothing but the same time complexity as of our same time complexity and space complexity as we do in our topological sort, or we can say our Kahn's algorithm. So this is the question.